Hello everyone, welcome back to our channel gsipucmysuru. This is the fourth session of the fourth chapter, feedback in amplifiers. In the last three sessions we discussed what exactly is the meaning of feedback, different types of feedback and different types of negative feedback, and we also derived an expression for the voltage gain of a voltage series negative feedback. In today's session we will be dealing with the input impedance and the output impedance of a negative feedback circuit. So let's begin this session with the increase in the input impedance. Increase in input impedance. We know that the input impedance for an amplifier circuit must be high. So, in order to increase the input impedance of a amplifier circuit, we are going to use a voltage series negative feedback circuit, and with the help of a voltage series negative feedback circuit, the input impedance of a circuit will be increased. So, let us take this circuit, basic amplifier, which is having a gain of A. And here I will be having one feedback network which is having a gain of beta. Here we will be having a load resistor RL across which the output voltage will be calculated, and the voltage will be fed back to the input. So, we will be extracting a portion of the output voltage and we will be connecting back that to the basic amplifier through this feedback network, and here we will be having an input source which is denoted by Vs, and the output voltage what is being extracted from the RL, that will be given to the feedback amplifier in series. So, that connection will be like this. So, this is a simple circuit of a voltage series negative feedback circuit, and the input voltage what is got across these 2 points is Vi, and the input current is nothing but Ii. This is the feedback voltage which is nothing but Vf, whose value is equal to beta times of V0. Beta is equal to output voltage divided by input voltage. The output voltage from the feedback network is Vf and the input voltage for the feedback network is V0. So, beta is equal to output divided by input. Output is Vf and input is V0 for this feedback network. So, if I am going to alter this expression, I will be getting Vf is equal to beta times of V0. That is what has been written over here. So, for an amplifier circuit, as I have told you, the input impedance must be very high. Then that will not load the preceding stages or the input voltage sources. So, in order to avoid the loading of the preceding stages, that is, in any of the circuits, an amplifier will be in the middle of the circuit. Before the amplifier will be having a number of blocks, and even after the amplifier will be having some other blocks. If the input impedance of this particular amplifier is very high, then that will help in avoiding the loading of this previous stage on this particular amplifier. So, what we have to do is, we have to maintain a high input impedance in the amplifier circuit. So, in order to get this characteristics, or in order to get this desirable characteristics of an amplifier, we are going to use this voltage series negative feedback circuit. So, in this circuit, the input impedance which is denoted by Zi, when the feedback network is not considered, that is, the input impedance of a basic amplifier, the input impedance of basic amplifier is given by Zi. Here Zi is nothing but the input impedance of a basic amplifier when feedback is not considered, and when feedback is considered, or the input impedance of the overall amplifier circuit will be denoted by ZIF, and II is the input current to the basic amplifier circuit, Vi is the input voltage for the amplifier circuit, V0 is nothing but the output voltage, Vf is nothing but the feedback voltage. So considering all these parameters, the input impedance of a basic amplifier circuit will be given as Zi is equal to Vi divided by Ii. We know that V is equal to I into R. Here we are talking in terms of impedance, so V is equal to I into Z, or Z is equal to V divided by I. Since we are talking about the input impedance, we have to consider the input voltage as well as the input current. So the input impedance of a basic amplifier circuit, which is denoted by Zi, is equal to the ratio of input voltage to the input current. Now the input impedance when feedback is considered, it will be denoted by ZIF. Without the feedback, the input impedance will be denoted by Zi, and with the feedback, the input impedance will be denoted by ZIF. Again, which is the ratio of voltage divided by current. Since I am talking about the input impedance, it is the ratio of input voltage to the input current. So when the feedback is considered, the input voltage will not be taken as Vi, the input voltage must be taken as Vs. Because once when the feedback network is considered, the output voltage will be equal to V0, whereas the input voltage will be equal to Vs. If the feedback network is not considered, then the input voltage for this basic amplifier is Vi and the input current is Ii. So accordingly, when considering the feedback network, the input impedance, which is denoted by ZIF, is equal to input voltage, which will be equal to Vs divided by Ii. So ZIF is equal to Vs divided by Ii. Now let us mark these two equations as equation number 1 and equation number 2. Now the net input voltage for the basic amplifier circuit, which is equal to Vi, is nothing but the difference between these two voltages. That is, the input voltage Vi is equal to Vs minus Vf. Why I am writing this negative symbol? Because I am taking a negative feedback circuit. If a positive feedback circuit was considered, then the net input voltage was equal to the sum of these two voltages, Vs plus Vf. So Vi is equal to Vs minus Vf, but I know that Vf is equal to beta into V0, Vs minus beta into V0, because Vf is equal to beta into V0. Then we know that the open loop gain A is equal to V0 divided by Vi. If I am going to alter this expression, I will be getting V0 is equal to A into Vi. So let us substitute for V0 in this particular expression. So Vi is equal to Vs minus beta into A into Vi. So let us take this term to the LHS, Vi plus A beta Vi. Here to the right hand side, this term is carrying a negative sign. When it is taken to the left hand side, the sign will change, is equal to Vs. If I am going to take Vi as the common factor, 1 plus A beta will be present within the bracket, which is equal to Vs. So let us substitute this expression, that is Vs is equal to Vi into 1 plus A beta in equation number 2. So ZIF now will be equal to, now I have to substitute Vi into 1 plus A beta in place of Vs. So Vi into 1 plus A beta whole divided by Ii. But according to the first equation, Vi by Zi is nothing but, Vi by Ii is nothing but Zi. So in place of this term, I am going to replace that term by Zi into 1 plus A beta. So finally, I will be getting the expression, that is the input impedance when the negative feedback is considered, ZIF is equal to Zi into 1 plus A beta, where Zi is nothing but the input impedance when the feedback is not considered, and A is nothing but the open loop gain, and beta is nothing but the feedback factor. From this final expression, we can easily tell that the input impedance will be increased by a factor of 1 plus A beta. So, we can easily increase ZIF is nothing but the input impedance when the feedback is considered. Zi is nothing but the input impedance when feedback is not considered. So, if I want to increase the input impedance of a given amplifier circuit, then we have to connect the circuit or use the negative feedback amplifier, and by doing so the input impedance of a feedback amplifier circuit will be increased by a factor of 1 plus A beta. So, with this we can easily tell that in order to increase a input impedance of a feedback amplifier, or in order to increase the impedance of a amplifier, that too input impedance of a amplifier circuit, we have to consider a voltage series negative feedback circuit. By doing so, we can easily increase the input impedance of a amplifier circuit, which is very important parameter, or which is very important characteristics of a amplifier circuit. Now let us see how to decrease the output impedance of an amplifier circuit. We know that another important characteristics of an amplifier is the output impedance of that amplifier circuit must be very low. By doing so, the power loss or the voltage loss will be very small. That is an amplifier with low output impedance will be having a capability to deliver the voltage or power to the load without much loss. So, that is a very important criteria what is required in an amplifier circuit. That is, whatever the output is coming from an amplifier, that has to be delivered to the next stage of an amplifier circuit. I can either use a multi-stage amplifier circuit or some other stage of a complete circuit, as we have seen in the transmitter circuits in the modulation and demodulation. There we will be seeing a number of different blocks. So, an amplifier will be present in the middle of the entire block diagram. So, whatever the output of the block diagram is, whatever the output of an amplifier is, that output voltage must appear as the input in the next stage of the circuit. The voltage or the power loss must be very small. In order to do that, we must make sure that the output impedance is very small. So, in order to get this desirable characteristics, we are going to use a voltage series negative feedback circuit. A voltage series negative feedback circuit is nothing but two blocks, where one of the block is a basic amplifier and the other block is a feedback network, provided the input source must be shorted. Now let us draw the diagram which is used in order to decrease the output impedance of an amplifier circuit. Here I am having a basic amplifier block. Below that I will be having a feedback network. This is the feedback network which is having a gain of beta. I told you the input source must be shorted. Vs must be equal to 0. So, this is what is very much important to decrease the output impedance. Here within the amplifier basic amplifier block, we will be having a circuit like this. This is nothing but the gain which is equal to A into Vi, and this will be considered as Z0, that is the output impedance, and the current which is flowing into the circuit is Ii, and the current which is flowing into this circuit is I0, and let me consider this as V0, and this will be fed back in this manner. So, this is the block diagram what we are going to use in order to decrease the output impedance of an amplifier circuit, which is a very important criteria in order to get the correct output, or in order to get the efficient output at the amplifier circuit. Here in this diagram, our output source V0 will be connected across the output. II is nothing but the input current. Vs is nothing but the input voltage which will be shorted. I0 is the output current, V0 is the output voltage, Z0 is nothing but the output impedance, and A into Vi is nothing but the output voltage, that is A into Vi is nothing but V naught. So now what we have to do is we have to apply KVL for this particular loop. If I am going to consider this as a source, V naught as a source, and whatever the voltage that is appearing across, or whatever the voltage I am applying with the help of V naught, that voltage will be shared among these two parameters, that is Z naught and A into Vi. That is, this voltage will be equal to the sum of the voltage drop across these two terms, A into Vi and Z naught. So let us apply KVL for that particular loop, but before that the output impedance of a circuit which is having a negative feedback network will be denoted by ZOF, which is equal to V naught divided by I naught. Let us consider this as equation number 1. And we also know that the voltage Vf is equal to beta into V naught. Now let us apply KVL. Let us apply KVL to the outer loop, to the output loop. Then according to that, V naught will be equal to A into Vi plus the voltage drop across Z naught is equal to the product of current and that impedance value, that is I naught into Z naught. Let us call this as equation number 1, and this is equation number 2. And the net input for the basic amplifier block, this is the basic amplifier block, let us call this as Vi. So the net input for this basic amplifier block is equal to the net input Vi will be equal to Vs minus Vf, but we know that Vs is equal to 0. So accordingly Vs will be equal to Vi will be equal to minus of Vf. So now let us substitute Vi as minus Vf in this second equation. Then I will be getting V naught is equal to I naught into Z naught minus A into Vf, because in place of Vi I am substituting minus Vf. So A into Vi will be equal to minus A into Vf. But we know that Vf is equal to beta times V naught. So V naught is equal to I naught into Z naught minus A into beta into V naught. So let us take this expression to the left hand side. V naught plus A beta V naught is equal to I naught into Z naught. If I take V naught as the common factor, then I will be getting 1 plus A beta is equal to I naught into Z naught. Then V naught by I naught, I am just cross multiplying this, V naught divided by I naught is equal to Z naught divided by 1 plus A beta. But according to the first expression, V naught by I naught is equal to ZOF. So ZOF is equal to Z naught divided by 1 plus A beta. So this is the final expression what we are going to get from this particular diagram. So according to this formula, according to this equation, ZOF is equal to Z naught divided by 1 plus A beta, we can easily tell that the output impedance of a negative feedback circuit will decrease by a factor of 1 plus A beta. So in order to increase the input impedance of an amplifier circuit, we are going to give a negative feedback connection, and in order to decrease the output impedance of an amplifier circuit, again we are going to give the negative feedback to the amplifier circuit. So by using this negative feedback circuit, we can increase the input impedance of an amplifier circuit as well as we can decrease the output impedance of an amplifier circuit, which are the most two important criteria or which are the most two important characteristics of an amplifier circuit. So from this equation, we can easily tell that we can decrease the output impedance of an amplifier circuit by giving the negative feedback circuit, and the output impedance will decrease by a factor, that is 1 plus A beta. Now let us see the frequency response of a negative feedback network. So what is this frequency response of a negative feedback amplifier? We know that frequency response is nothing but a graph which is plotted between the frequency and the voltage gain of a circuit. If a negative feedback is connected for an amplifier circuit, then we have already seen that the voltage gain of the negative feedback circuit will decrease by some factor. So now let us try to analyze the frequency response of this negative feedback amplifier circuit with this diagram. We are going to take a frequency response curve where I am plotting frequency on the y-axis, on the x-axis, and voltage gain on the y-axis. Frequency will be plotted on the x-axis and voltage gain will be plotted on the y-axis. If I am going to consider this as the voltage gain curve or the frequency response curve before the feedback network. Before feedback, let me write it as FB. This is the maximum gain. Let us denote it by A max, and 3 dB decibels gain, or 3 dB gain of this is nothing but 0.707. 707 A max is this, and the frequencies of this 3 dB will be denoted by F1 and F2, where F1 was called as the lower cutoff frequency and F2 will be called as the higher cutoff frequency. And we know that the gain of the amplifier circuit will decrease to a small factor when the feedback is connected or when the feedback is considered. So the gain of a feedback circuit will come below this, and let us denote the gain of this as AF max, and 3 dB gain will be this, which is nothing but 0.707 AF max, and the 3 dB frequencies will be denoted by F1 dash and F2 dash. Why 3 dB gain will be considered in an amplifier circuit was already discussed in the previous chapters. So, the gain of a feedback circuit will decrease. So, we have drawn the frequency response curve of a feedback network below the frequency response curve without taking the feedback. So this is the frequency response curve, that is the comparison of the frequency response curve between a circuit without connecting the feedback network and a circuit by connecting the feedback network. And the bandwidth of an amplifier without the feedback is equal to separation between the 3 dB frequencies, that is F2 minus F1. So bandwidth without feedback is denoted by BW, which is equal to F2 minus F1, where F1 is nothing but the lower cutoff frequency and F2 is nothing but the upper cutoff frequency, or it is also called as lower 3 dB frequency, and F2 is called as the upper 3 dB frequency. And if A is considered as the gain, if A is gain, then gain bandwidth product, gain bandwidth product of a circuit without giving the feedback connection is A into bandwidth. Now, the bandwidth with feedback, the bandwidth with feedback is denoted by BWF. Then the lower cutoff frequency will decrease by a factor of 1 plus A beta, and the higher cutoff frequency will increase by a factor of 1 plus A beta. That is, F1 dash will decrease in the sense F1 divided by 1 plus A beta, whereas F2 dash, which is the upper cutoff frequency of an amplifier circuit when the feedback is considered, will increase by a factor of 1 plus A beta in the sense F2 into 1 plus A beta. Whenever we are going to tell that it will decrease, then that term must be written in the denominator. Whenever we tell that the bandwidth or the frequency will increase by a factor of 1 plus A beta, then that term will be multiplied. So these are the two frequencies, that is the lower cutoff frequency and the upper cutoff frequencies of an amplifier circuit when the feedback is considered. Then the new bandwidth BWF will be given as F2 dash minus F1 dash. That is, when the feedback is considered, the bandwidth will be equal to f2 dash minus f1 dash, where f2 dash is nothing but the upper cutoff frequency and f1 dash is considered as the lower cutoff frequency. And the relationship between the bandwidth of amplifier circuit with and without the feedback network is given by the formula BWF is equal to BW into 1 plus A beta, where BWF is nothing but the bandwidth of an amplifier circuit when the feedback network is considered. BW is the bandwidth of an amplifier circuit without feedback. A is the open loop gain and beta is nothing but the feedback factor. But in both the cases in the sense when a circuit is having a feedback or not having the feedback, then the gain and the bandwidth product will remain the same. Gain and bandwidth product in the sense A into BW will be equal to AF into BWF, where A is nothing but the open loop gain, BW is nothing but the bandwidth of a circuit without the feedback, AF is nothing but the feedback gain, that is the gain of a circuit when feedback is considered. BWF is nothing but the bandwidth of a circuit when feedback is considered. So these are the terms what you have to keep in mind when we talk about the frequency response of a negative feedback amplifier. We already know that the gain of a negative feedback amplifier will decrease to a smaller extent, but the gain and the bandwidth product will remain the same, either we consider a circuit with feedback or without the feedback. So I hope you are very much clear that how we are going to increase the input impedance of an amplifier circuit and how we are going to decrease the output impedance of an amplifier circuit, which are the very two important characteristics of an amplifier. So in the next session, I will be solving some of the problems on these particular topics. Thank you.